So, right, dear friends, I guess we can smoothly start. It's my pleasure to introduce our today's guest, Dr. Junu Jeong, who comes from South Korea, Center for Axion and Precision Physics Research in nice city of Daejeon. So he's presenting the activities of relatively big center related to recent search results of axions, which might constitute whole dark matter. This is a hypothetical particle. So Junu, please, you are welcome. The stage is yours.
Okay. Thank you very much for introducing me. Hello, I am Junu Jeong, postdoctoral researcher at CAPP. First, I would like to thank Professor Maxim for giving me the opportunity to present CAPP's latest search result today. Then I will start the presentation about the search result for the CDM action searches at CAPP. Here is the outline of my talk. First, I will introduce the axion and dark matter axion, and I will explain Axion Haloscope, which is a way to search for dark matter axions. And after that, I will present the CAPP Haloscopes, which is our CAPP's Axion Haloscope. And finally, I will talk about CAPP's other R&D efforts. First, I will present about axion and dark matter axions. Let's think about neutron for a moment. As we know that neutron is a particle in which composed of UDD, 3 quarks, are condensated, and the net charge is 0. And also, we know that neutron have a spin 1/2, and naturally, it also has a non-zero magnetic moment, mu, and the direction of this magnetic moment is parallel to the spin. And we can directly think that U quark and D quark has different charges. So if there is some spatial separation of charges, then an electric dipole moment of neutron can be possible. So we can ask that does a neutron also have an electric dipole moment as well as the magnetic dipole moment? In fact, the standard model predicts the neutron will have an electric dipole moment. In QCD, which describes the physics of the quark and gluon, there is a Lagrangian density term called zeta term, and this term gives the effective charge separation. The degree of this charge separation is described by the zeta bar here, which can have a value between 0 and 2 pi. Here G is the gluon coupling constant, and large G is the just gluon field. Then the magnitude of the neutron's electric dipole moment can be estimated with this amount, which is about 3 times 10 to minus 16 zeta bar electric centimeter. And the direction is also parallel to the spin direction, because the direction of the vector property that has spin 1/2 particle can have is only the spin direction. And since the magnetic dipole moment and the electric dipole moment, the relative direction are reversed for parity transition and charge parity transition. So having both of these electric and magnetic dipole moment means that the parity and CP symmetry of this theory or the universe is broken. The zeta bar is actually given as the sum of the instantaneous effect, which is coming from the gluon's vacuum state, and also the Higgs mechanism effect, which is from the weak sector, which is the phase of the quark mass matrix. Both of these effects can have a random value between 0 and 2 pi in nature. And since the zeta bar is just sum of these two phenomena and that appear completely independent of each other, the zeta bar is also predicted to have an order of 1. However, many experiments have tried to measure the EDM of neutrons, but so far, no evidence has been found. And it appears that the strong interaction looks like preserving the CP symmetry. The current limit for neutron EDM is about 2 times 10 to minus 26 electric centimeter, and this implies that the zeta bar should be less than 10 to minus 10. This is called the strong CP problem, and it is a fine-tuning problem that the zeta bar was predicted to be an order of 1 in theory, but we obtained a value very close to 0 experimentally. Peccei and Quinn have proposed an elegant way to solve this problem, which is called Peccei-Quinn mechanism. They noted that this zeta bar Lagrangian term that breaks the CP symmetry has the lowest energy when the zeta bar is placed at 0. So they came up with the new idea that the zeta bar could be a dynamic field rather than just a constant. Actually, it is difficult to add any dynamic field to the instanton effect, but it is possible to create a model that has a dynamic field to the phase of the quark mass matrix. Then as the universe expands, the dynamic field naturally seeks the vacuum, which is the lowest energy state, and it can explain the current small zeta bar. And actually, the small oscillation of this zeta bar is the axion. The representative models that has a dynamic field into the phase of the quark mass matrix are the KSVG model and the DFSG model. The KSVG model assumes the additional heavy quark, and that quark undergoes a process similar to the Higgs mechanism through the new PQ scalar field. And it adds an axion into the quark mass matrix by this heavy quark's phase. And the DFSG model assumes two Higgses, and the phase difference between these two Higgs serves as an axion. The PQ scalar field in those models can undergo the spontaneous symmetry breaking, SSB, at arbitrary high energy scale. We usually say FA. And this gives the invisible axion that interacts feebly with other particles. What makes axion interesting is that they can also address another conundrum of modern physics, the dark matter mystery. Dark matter is a unknown particle that does not interact with light, but is gravitationally necessary. The evidence for dark matter is substantial, but here I brought only two representative evidence. One is the galaxy rotation curve, and the other one is the black cluster. From the galaxy rotation curve, from the visible particles, the expected rotation curve gradually decreases as it goes to tail, but what we measure is that it has the constant velocity even it goes to tail. And this means that there's to be some missing masses. And second one, the black cluster, is the two colliding galaxies, and we can get the mass distribution from the light and also from the gravitational lensing effect through the background stars. So these two distribution shows clear distinct, and which means there is masses that we cannot see. The invisible axion is one of the strong candidates for dark matter because it feebly interacts with other particles, and in particular, if the mass is less than 10 millielectron volt, there can be a sufficient amount of cold state from the beginning of the universe, which acts as a dark matter. And the origin is the initial zeta bar and the topological defect of the SSB or PQ scalar field. Now I will describe the most.
Juno,
yes.
May I ask you a short question regarding the previous slide? So some time ago, people were looking at these weakly interacting massive particles as also some potential candidates for dark matter. So
right.
What has changed, and why people put less emphasis on this potential candidate? Could you?
So people did a lot of effort to search for WIMP from 2000 to from the 2000 years and 2000, but there was no evidence. I mean, there was one evidence claim that which institute was that? Anyway, except one institute, all of the other institutes could exclude the possible WIMP masses with their sensitivity, but there is still allowed regions. But even if WIMP is true, the people think it could be detected from those other experiment, or also through the some, what can I say, some collider physics also could see some evidence, but we could not see yet, but it could be WIMP, but we don't know yet, but still people then looking the other side also now. So
yeah.
actually,
But just to understand the scales, so what are the expected masses of these WIMP particles?
masses. Yeah, I see. So I'm sorry. So for the Axions, it is expected to have mass below milli-electron volt level, but the WIMP has the mass above giga-electron volt.
Oh, okay. So very heavy,
totally different.
boson.
Yeah. And WIMP is actually fermion, so but Axion is boson. Yeah, these are different.
Thanks.
Yeah. So now I will present about the most sensitive way to prove dark matter actions, which is the Axion Haloscope. First, let's understand how actions interact with photons. The action has a gluon coupling coming from the CP bilateral Lagrangian, which looks like this. This term is just a replacement of zeta bar with A over FA. A is the action field and FA is the symmetry breaking scale. And then at the low energy scale, this kind of interaction is can give this kind of Axion-Photon interaction, and in the form of A E dot B, where GA gamma gamma is the action to photon coupling strength, A is the action field, E is the electric field, and B is magnetic field, and the origin is this kind of triangle Koch loop. And if we apply the least action principle, including this Lagrangian density, then and write the photons equation of motion, then we can get this kind of modified Maxwell's equation with some additional charge densities and current densities. So the action actually interacts with the electromagnetic fields to induce additional this kind of charge and current densities. And for cold dark matter, by definition, the spatial derivative is much smaller than the temporal derivatives. So these spatial derivative terms are can be neglected in Haloscope. Let's consider a situation where a magnetic field is applied with a solenoid, as shown in this kind of figure. Then a vacuum current density oscillating in the direction parallel to the applied magnetic field is induced by the background dark matter action. If we bring a microwave cavity with a resonant frequency that matches the oscillating this current density, which is the action frequency, then this vacuum current density can accumulate in the cavity, and the Axion-Photon conversion is amplified. The conversion power is given like this. These blue parameters are the theoretical parameters. GA gamma gamma is the Axion-Photon coupling, rho is the dark matter action density, and m is the action mass. And it's proportional to the applied magnetic field square, volume of the cavity, and cavity Curry factor, and finally the form factor, which describes the degree of the alignment of the applied magnetic field with the electric field of the cavity mode.
Yeah, so Junu, may I ask a question here as well? So I wonder where people catch the photons inside the cavity, because I guess depending where you try to measure the signal, the outcome would be different.
I'm sorry, could you
so
repeat that?
Where do people detect the photons, which are expected from conversion of dark matter to photon?
I see. So photon is the most, one of the easiest way to acquire the data. But there are several other experiments try to measure the spin of the fermions, spin of electron or spin of helium nuclear. And if we align those spins, and if some axion wind touches those spins, then it can have some precision. And there is some experiments that are trying to measure those kind of spins, but
but here in this type of experiments with Haloscope, how do they detect photons?
So how do we detect the photons, you mean?
So where do they put detectors for photons?
So yeah, I will explain in the next slide. So,
okay. Thanks.
Yes, this kind of experiment was first proposed by Peccei-Quinn in 1983 and is still widely used today. And as just Professor Maxime asked, we attached an antenna, photon antenna, and also some readout electronics to it. Then we can read some, if there is some photon is came out, then this kind of photon is transferred to this readout electronics, and we measure the voltages. So that looking for the evidence of dark matter action by this kind of vacuum current density. Is okay to your answer?
Yeah, fine, thanks.
Okay. And also, since the mass of the axion is a priori unknown, we have to put a tuner inside the microwave cavity that can tune the resonant frequency of the microwave cavity, because this conversion is only enhanced when the axion frequency and the cavity frequencies are matched. So how fast we can cover the given axion parameter space is called the scanning rate, and this has proportionality like this, and this is the figure of merit of the experimental setup. Here, T system is the system noise temperature, and is the sum of the summer noise portion and the noise temperature of the added noise temperature by this kind of readout electronics. And this plot shows the axion parameter space that has been excluded through several Axion Haloscopes to date, and the yellow band in the center is the area predicted by the theory. And there are two lines, KSVG and DFSG models. And as you can see, various groups around the world are conducting experiments for axion searches. And the red area here are the excluded regions from our research center, CAPP, and I will explain what experiments were performed in the next following session. So let's move on to CAPP Haloscopes.
Excuse me,
Yes.
may I ask a question about previous slide?
Okay.
Yeah,
Yeah.
as I see, there's like not a very wide range of the parameters which predicted by theory, but like the most of the experiments don't lie in this range. Why are people still trying to find some actions in the range which is not predicted by theory?
Yeah, that's a good question. So actually, this is the action if detected in these regions, they are called QCD action, which can explain the strong CP problem. But people think that there could be some action-like particle that not necessary to solve the strong CP problem, but can have the same interaction, something like the action as having like this kind of form. So if there is certain unknown field that have this kind of field, that then this kind of form, then it is called axion-like particle, and which is also very interesting hypothetical particle that could address the dark matter. So that's why people are still looking for the other white regions.
Yeah, okay, thank you very much.
Yeah, you're welcome. So here is the brief introduction to CAPP. CAPP is the Center for Axion and Precision Physics Research, and is the research center of the Institute for Basic Science. And our main project is the search for dark matter actions, and we are located at KAIST Munji campus now. And we in Korea, and we installed 7 low vibration pads in this building to conduct the parallel experiments. This photo shows the current experimental space. There are several magnets and fridges where they are installed on the floor on top of the low vibration pad, and we are trying to conduct the parallel haloscope experiments. And each location from the left is experimental space for CAPP-90MC and CAPP-12TB and CAPP-PACE and CAPP-ATB. So our research center is operating in total 7 refrigerators for R&D. And in order to improve the scanning rate, we have to lower the system noise temperature, which means we have to lower the physical temperature. That's why we are operating several dilution refrigerators, which have the tens of the millikelvin of the base temperature. Also, for the Axion-Photon Interaction, high magnetic field is required. So for that, we have installed 6 magnets in each dilution refrigerators. And among them, the bottom line, the 12 Tesla 320 millimeter Bohr's magnet is the most prominent system in our research center. And for each system, we have conducted the experiments. Those experiments, those six experiments have published all the results in PRL. And each of the experiments exclude the documented actions with the highest sensitivity in each target frequency regions. And there is one more, is preparing experiment with this system. After lowering the physical temperature using the refrigerators, we also lower the noise temperature as much as possible by developing readout electronics. So we employ the flux-driven parametric amplifiers, which can go down to the near the standard quantum limit, which is the limit for the linear amplifier, and it parametric amplifies the incoming wave through the skid loop on here like this. And for a few gigahertz regions, it has around 200 millikelvin noise temperature. And also we design our in-house 3-layer magnetic shield, aluminum, mumetal, and niobium, something like this, and it makes the JPACE not to be almost affected by the external magnetic environment. Then first, I will introduce the CAPP-12TB, which is the flagship experiment of our research center. The CAPP-12TB uses a magnet with a central magnetic field of 12 Tesla and bore diameter of 320 millimeter, which gives about a huge magnetic energy, about 5 to 6 megajoule. And it also improves the dilution refrigerator, which can cool the physical temperature to 25 millikelvin. And we also put this kind of huge cavity that has volume more than 30 liters and also coil factor more than 10 to 5. And for the readout electronics, we employ the Josephson parametric amplifier, as mentioned before, which has about 200 millikelvin noise temperature. And assembled with this state-of-art equipment, this CAPP-12TB experiment has a great scaling rate. I will explain. So for the KS rejection in this system, produce about 1,000 photons per second if the resonance meets. And likewise, the DFSG Axion produce about 100 photons per second in this system. And currently, we could reach the 200 millikelvin of the system noise temperature. And this gives us the scaling rate of the 50 gigahertz per year for the KS rejections and 1 gigahertz per year for the DFS rejection. And this system also has a potential to speed the DFSC actions to 4 gigahertz per year if we could further improve in the JPA, reaching the noise temperature of near the 100 millikelvin. Especially for the CAPP-12TB, we have developed an ultralight cavity. In past, cavity was made by processing bulk copper and assembling it, but the volume of this system was too large, so the mass was also too large. And at first, the training system was not operated well, so we changed the design that the thin copper sheet, we roll the thin copper sheet like this, and we put the end caps on there, making this kind of very light cavity. And through this, we could have a very volumetrically efficient design without the loss of the coil factor. And the weight is also very light. Even it has about 37 liter volume, the total mass was less than 6 kilogram. And as the mass is reduced, the heat capacity of this cavity is also reduced, and the temperature of the cavity also went down well to 25 millikelvin.
So, Junu, may I ask a question regarding the previous slide, maybe?
Yeah.
So, even if you go one slide back.
One slide back.
Yeah, here. So, what's kind of the detection scheme for photons? I guess you have relatively large fluxes of photons. So, do you need single photon detectors, or you don't?
Yes. yeah, single photon detector is very good approach. So if it is applicable for these frequency regions, but unfortunately there were no available single photon detector in these frequencies. The state of art single photon detector could reaches about for 30 gigahertz or 50 gigahertz photons, but not few gigahertz photons. That's why we are currently using the linear amplifier, not just that bolometer type or the photon counter type.
Right,
okay.
Thanks.
Yeah. Okay, this is the result of the last year's run through the CAPP TV system, and it was recently published in PRL. And we searched for documentary actions at the DFSE sensitivity like this. We searched for 20 megahertz for this run around 1.1 gigahertz, and since there was no abnormal signal detected in this area, so documentary action in this area was excluded with a 90% confidence level. We also, after this run, we subsequently acquiring data over wider frequency ranges, and we already have explored close to 150 megahertz, and it is expected to be end by the middle of this April. We are currently acquiring data with a scanning rate of 3 megahertz per day, and after this run is over, we will replace the cavity and JPAs that can cover above 1.2 gigahertz and then continue the run. Early this year, we published DFS sensitivity run on PRL, and we took the photo together like this. And everyone here are passionately conducting this experiment to search for documentary actions together. Next, I will briefly introduce the rest of CAPP Haloscopes. These experiments are different in detail, but the principle of the experiment is the same in the big picture. So I will only briefly introduce each experiment and briefly. And in addition to those experiments here, there is also CAPP-18T experiment, which was performed in other room, not shown in this picture, but still the big picture is the same. So I will skip the detail of that experiment also. So first, the CAPP-ATB experiment, which was conducted about 4 years ago, 4 years ago, maybe. And it employs 8 Tesla AMI magnet and blue force dilution refrigerator. And we could reach the cavity temperature around 15 millikelvin. But at the time, we couldn't employ the JPA, but we used the HEMT, which is the high electron mobility transistor, which has the noise temperature of 1 Kelvin. So which gives not as good scanning rate when comparing to JPA run, but still we could reach the 4K SVG coupling, and we explore 50 megahertz range or near the 1.6 gigahertz through this system. And second one is the CAPP-90MC experiment. This is the proof of concept experiment newly developed for the newly developed multiple cell cavity, and which is for high mass action searches. This system also has a relatively high noise temperature, physical temperature of 2 Kelvin, and the added noise temperature of 1.5 Kelvin. But still, this was a proof of concept experiment. We just conduct the first multiple cell Haloscope experiment using this kind of multiple cell cavity. Actually, in this case, it was 2 cell, but the figure is 6 cell. And using this system, we could explore around 3.3 gigahertz regions and for the 10K speed couplings. And the detail of the multiple cell cavity will be discussed in the next section. And the last one is CAPP-PACE, which is our research center's pilot experiment team. And this through this system, we first conducted Axion Haloscope experiment in our center, and it also employed JPA at first. And this system used a similar magnet as ATB, but smaller size, and also physical temperature was reached to 40 millikelvin. And through this system, we could cover 2.5 GHz regions with 10 KSVG coupling. And this plot shows the exclusion limits for each experiment. Here, this line is the CAPP-ATB, and this region is CAPP-PACE, and this one is CAPP-90MC. Finally, I will present the CAPP's other R&D efforts. In this section, I will present the development of cavity design for high-frequency searches and the development of the superconducting cavity for high-query factor cavities. The cavity is the most sensitive method for axion detection in the microwave regions, but it's becoming less efficient in the high-frequency regions because mainly due to the volume loss. For example, if we increase the target frequency 2 times by reducing the cavity radius by a factor of 2, while keeping the aspect ratio, then the scanning rate is reduced by a factor of 100, which is very huge amount. So that's why people are currently running the experiments relatively low frequencies. However, since the axion masses can be placed anywhere below millielectron volt, this is the kind of preferred reason, but anyway, axion can be placed anywhere below the millielectron volt. So it is required to be able to search the axion even at higher frequencies. And searching only at the low frequencies is like expressed in this cartoon that looking for some loose wallet called Axion in the standard model park under the string lamp, bright string lamp. So we try to develop a flashlight that would be able to navigate in the high frequencies even it's dark. One of the methods is the multiple cavity design. Instead of having a small cavity radius, multiple cell cavity is introducing a metal partition like this, so that increase the resonant frequency. Up to here is actually just a kind of multiple cavity system, but the innovation of this design is introducing a small center gap at the center, which spatially connects all the cells together. And through this small gap, we can read out all the axion to photon converted photons through a single antenna, which simplifies the RF chain. And this picture shows the fabricated multiple cell cavity design. Here is 2 cell and here is the 4 cell. Utilizing this design, CAPP-90MC experiment was successfully conducted, and this attempt was made to search for dark matter axion near 3.3 GHz. And with this successful proof of concept experiment, we are now trying to make another complex multiple cell cavities that can install in other refrigerator systems. And we also have recently developed tunable photonic crystal for further higher frequency regions. And this photonic crystal is actually kind of a dielectric array. And the search frequency is determined by the spacing between those dielectrics. And this design has a high query factor and not bad form factor, but it was not used because there was no tuning method so far. But we found the answer of the tuning method in the exotic structure, which is inspired by origami. When we create a structure, something like this, then we just by rotating the center rod like this, we can adjust the overall photonic crystal spacing like this. And then the resonant frequency of the cavity can be tuned, something like that. So we designed this kind of demonstration cavity and fabricated it like this, and we could successfully tune this cavity at the 4 Kelvin and prove the feasibility of the axion search, feasibility of this design for the axion search experiment. So I will show the video how it works. So it is tuned something like this. Yeah.
So, you know, this setup works at the frequencies of the order of few gigahertz. What is the specific?
It is targeting 10 gigahertz.
Oh,
regions.
10. Oh, that's...
Yeah. Okay. We are also developing a superconducting cavity for more efficient scaling rate. As you can see in the scaling rate equation, it proportional to the Curry factor. So as the Curry factor increases, we can scan much faster than before. And as shown in this picture, we designed this kind of vertical cut sliced cavity, and we put a superconducting tape on the surface of this vertical cut cavity. Since we are improving the TM010 mode, this kind of vertical cut almost doesn't affect on the Curry factor of the total assembled cavity. Because we put the high temperature superconducting cavity, the Curry factor, the superconductivity is maintained even under the strong magnetic field. This plot shows that the superconducting transition occurs at around 90 Kelvin, and even we turn on the magnetic field up to 8 Tesla, the Curry factor is much higher than that of the copper with the same design. One point I would like to emphasize here is that our center developed the first superconducting cavity that work under a strong magnetic field. And we have been continuously researching and developing these kind of high Curry factor cavities. And the first generation is this kind of melon-shaped design, and we used the YBCO tape, and we could reach about 0.33 million under 8 Tesla. And we changed the design slightly like this, and we used the GDBCO tape, which is just different form of tape. And in this case, we could reach about 0.5 million. And now, after several tests with superconducting tapes, we confirmed that EuroBCO tape, which gives the most effective Curry factor among several superconducting tapes. So we developed the cavity like this, which this looks very beautiful. And we could achieve the remarkable Curry factor, 13 million, even under 8 Tesla. And this plot again shows the action parameter space that has been excluded by the various haloscopes so far. We are now trying to improve this kind of superconducting cavity and high frequency cavities to search this shaded area. This region will improve this high frequency cavities. And also CAPP-TB system is keep operated to search for the DFSG actions from 1 to 2 gigahertz, improving the JPA. Let me summarize the talk. So Axion is a hypothetical particle proposed to resolve the strong CP problem, and the invisible action is the one of the strong candidates for the dark matter. And Haloscope, CAPP Haloscope or Axion Haloscope is the most sensitive method to search for dark matter actions in the microwave regions. And we are one of the world leading groups of CDM action searches. And CAPP-TB reaches the DFSG sensitivity with the large volume, strong magnetic field, and also the low noise temperature readout chain. And we are running several haloscopes in parallel and operating several dilution refrigerators and Josephson parametric amplifiers with low noise temperature. And we developed the multiple cavity and tunable photonic crystal for high frequency searches, and also superconducting cavities for high quality vector cavities, which improved the scanning rate further. Thank you very much.
Thank you so much, Junu. So now the talk is open for questions. Maybe I will start from the first one. So describing your flagship project, you mentioned that you scanned the frequencies around 1.09 gigahertz, something like that. So I wonder what was the specific reason for choosing this frequency. It seemed that you could also choose, let's say, 1.1 or 1.2, so it's more or less the same. So, so what was the reason to choose some specific frequency range? So
for the CAPP-TB system, you mean?
Yeah, for this flagship project, where you scanned some range of 20 megahertz.
Yeah.
So.
Thank you for the question. Actually, the natural frequencies naturally determined by its radius. So if the magnet has certain Bohr diameter, and we would like to fully employ those volume, then the radius of the cavity is determined, and this radius actually give us the frequency.
Good. So everything comes from the magnet. If you have bigger magnet, then you can work with other frequencies, but like magnet dictates.
Yeah, but as I presented like this, this kind of new designs or this kind of photonic crystal design can target any frequency, higher frequencies, even the magnet diameter is fixed. So that's one good thing of this kind of design. We can target certain frequency, through this kind of.
Thank you. And then one more related technical question. You were saying about several types of magnets. In all cases, the magnetic field is below 12 Tesla. So could you comment, please, whether it is possible to go to higher magnetic fields, or it's not available currently?
Yeah, it's a very good question. So those magnets are actually made by niobium. I remember niobium, and those have the critical magnetic field around slightly above 10 Tesla, I remember. But anyway, it is a huge amount of current is flowing. So the limit for the central magnetic field is around 8 Tesla or 9 Tesla. But if we employ the niobium 310, then we could reach around 12 Tesla, because niobium 310 has slightly more the critical field and critical current density. And for the 18 Tesla, this experiment, we actually employ the type 2 superconductor for the magnet. But it has very small Bohr diameter, but since the magnet employs the type 2 some high temperature superconductor rather than the niobium and niobium 310, which enables this kind of huge field strength.
Okay, thank you. So I see the limitation. You cannot go to high magnetic field because this implies strong currents, and they in turn destroy the superconductivity.
Right, exactly, yes.
And then maybe a general, a bit naive question. So as you said, people anticipate that gradients of axion field are negligible compared to time derivatives of axion field. So what are the considerations behind that assumption?
So it is actually the gradient of this kind of bosonic field corresponds to its velocity, and the time derivative of the field corresponds to its mass. And because we are looking for the cold dark matter, which has the velocity much smaller than the speed of light. So in the Axion case, in the dark matter around our solar system, it is expected to have a velocity of about 10 to minus 3 speed of light. So this means that the difference between these two have around 10 to minus 3. So that's why we could neglect those terms. But still, there are several experiments that they are trying to measure the wind of the axion dark matter.
And this is 1,000 times harder to do.
Right. Yeah.
And the assumption of cold dark matter comes just from astrophysics, as I understand. So it comes from cosmology.
Yeah, it comes from cosmology, right?
Fine, good. So, colleagues, do you have any other questions? Please, you have an opportunity now to ask. So, looks like no other questions. So, thank you, Junu, once again. Wish you good luck. Hopefully, someone will be able to find this axion in the nearest future. Don't we think
Thank you very much.
Yeah, at which frequency? That's the main question. Yeah. So wish you good luck with these searches, and so stay in touch. Hope to see you at some conferences in the future.
Thank you very much.
Yes. Yeah, goodbye.